what we just learned last week. And last week we just learned about the substitution, and especially it's just for indefinite integral. So what is a substitution? You can just use a u to replace a little bit complicated function, just like this. Then you can just simplify it into a simple form. Then it will be easier for you to do the calculation of the integral for this. Then you can use u is equal to g of x to replace. Then maybe originally the integrate form is a little bit complicated, but through this substitution, you can just make it become a simpler form. But just remember, when you just replace replace g of x with u, then also need to remember to replace dx. So that means once you just replace it, you need to measure from the beginning it will be blah 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 x also dx. After you replace it, please just make sure it should be with a form with blah 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 u, so that the mechanism is just like this. Once you just let u be g of x, please just remember, immediately calculate du over dx, so that through this you can know the relationship between du and dx, so that you can just have all of them in u form, so that finally you can get, after the calculation of the integral, then you can get blah blah u plus c, because it's a indefinite integral. So supposedly you need to plus c. Then also remember, after you have this, remember to replace u back to blah 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 x. So finally you will get blah 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 x plus c. Okay, this is for indefinite integral. And for the section 6, we also talk about the substitution, but this time we will discuss substitution in definite integral. So you can see that the only difference from here and here, you can have some simple comparison that in definite integral we will now have the limit of, that means the two ends for the integral. But if it's just for definite integral, of course you will have a and b, that means the two limits for the integral a and b. So very similar, if you just let u be g of x, remember immediately calculate du over dx, so that you can get the relationship between du and dx, then become this one. And also remember, for the substitution in definite integral, remember to change the two limits for the integral, because we will just follow the new form. Okay, so today I will give you an example first, so that you can just have some impression of the substitution for the definite integral. So okay, let me just show you an example that okay, so it will be integral from -1 to 1 3x squared times square root of s cubed plus 1 dx. Okay, so since you can see we have two limits for the integral, so it's a typical definite integral. So the solution one is just like that. we just simply because we just find this form is a little bit complicated, right? Because it's just under the square root, so it can make the calculation more complicated. So why now we just let u is equal to s cubed plus 1. So as I may remind you, always do that after you assign u to be s cubed plus 1, immediately calculate du over dx. Then you can get 3 square s square, so that you can get du is 3s squared times dx. So you can see we can get the relationship between du and the dx. So we can use this to replace here, right? To replace, we can use this to replace here, right? So the form will become integral square root of u then du, right? But this is just for indefinite integral. But remember, this is a definite integral, so we also change the limits for the integral. So here, my 1 should be replaced by 1 cubed plus 1, and minus 1 also through this one to become minus 1 cubed plus 1. So we can see, because you just use the new variable, it will be u. So it will be u, right? But don't forget, 2 bounds, 2 ends, 2 limits for the integral should be also changed. Then you can see that will be 1 plus 1 half plus 1 u to the power 1 plus 1 plus 1 1 half plus 1. Then that will be, here will become 2, here also will become 0. So with this, then you can continue to calculate. That will be 2/3 times 2 to the power of 3/2 minus 0 to the power of 3/2. So the answer will be this one. So the final result will be this one. Okay, so this is just a follow the mechanism for section 6, especially for the definite integral, right? So that you can see, we can just use u directly. We don't need to go back to x, because here we already changed the limits, change the 2 limits. Of course, we can follow. This is for section 6, right? And we also can follow this. In the beginning, you just still regard it as a indefinite integral. So did you notice I didn't put the limits here? This time I just treat it as indefinite integral first. So follow this. Again, you can just use that u is equal to, that u be equal to x cubed plus 1, then of course you can also calculate this, right? Very similar. For this step, very similar, right? And so that you can have this. So remember, since you just treat it as a indefinite integral, so the result will, you need to, that you be back to blah 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 x, so the final result will be this one. Right? So here, just follow the process in section 5. We just treat it as the indefinite integral first. Then after you have this, you already know your target is calculate definite integral. So we just put it back to put these two limits back to the integral form. So that will be, you already have your antiderivative, right? Then here will be minus 1 to 1, so that the result is still the same. Okay, either solution 1, make it small, you can have a simple comparison, right? For solution 1, you just change the variable by the replacement. But when you just replace it, because it's just a definite integral, you also need to change the end, to bounds, to limits. Okay? So the answer is just that. For solution 2, you just ignore the limits for the integral first. So you just treat it as a indefinite integral first. Of course, after the integration, you can get this antiderivative, right? So this is the antiderivative for this one. So after you have this, you have the antiderivative form. So when you just put the two limits for the integral back, that means negative 1 to 1 back. So you can just simply use the antiderivative you just got, then put two ends here, so that you can also get an answer. So either way is good. Okay? And then there is another theorem for that if f(x) be continuous on the symmetric interval, minus a to positive a. So it's a symmetric interval from negative a to positive a. So if f(x) is even, did you still remember what's the even function? The curve will be symmetric on the y-axis. Did you remember? Symmetric. If it's as a even function. So I can show you. The function will be, for example, if it's even function. The even function means if you have this to positive a, of course you have another part is this one, because it will be symmetric over the y-axis, right? So if so, if I ask you to calculate the integral from minus a to a f(x), then it will be 2 times integral from a to positive a, 0 to positive a, L of ds. So it's quite intuitive, right? Because it's symmetric. So if you have this part, of course, due to the symmetric property, you can also have the other part. So when you just take the integral from negative a positive a, of course, it's just 2 times of this part, right? Just 2 times of this part, right? Okay, if f of s is odd, if odd, we also know that the curve should be symmetric on the 0, 0, right? The origin. So the curve will be just look like this one. If we also have the curve just like this one, since it's odd function, so of course we have the same curve, but the symmetry to the origin, right? So if here is negative a, so the curve will just like this, right? So the same here, the size here will be the same as here. So if I ask you to calculate, what's the result? What's the result? What's the result? 0. 0, right? Because the size here is totally equal to this part. But here is positive part, but here is negative part. So they will deduct by each other. So the result will be 0. So when you can find a function can have the symmetric property, no matter it's even or it's odd, you can just follow this rule, these 2 rules, so that they can save some effort for you to calculating the final result. So I will give you a quick example. But please notice only the index, only the bound for the integral is symmetric. It will be used for otherwise, and at the same time it should be an even function or odd function. Otherwise you cannot do that. Of course you can still follow the original one to do, but if we just follow the symmetric property, it can save some effort for you. Okay, so if we do this, okay, when we just calculate this one, you can see s to the power 4. It is even or odd. S to the power 4, even or odd. Even or odd. Even, right? Even function, right? It's a even function. And how about minus 4s squared? Even or odd? Even. Also even, right? For 6 constant function. Even. Even minus even plus even. So in total, it is still even. So if it's even, we can just follow this rule. We can just calculate the help part. Then times 2. Right? So for you, if you can have an index, if from the n is 0, you can see the calculation can be simplified. So finally, I will not go to the details, but I just give you the final answer, just like this. Okay, but the property only can be applied when you can find the symmetric properties for the integral. And okay, then we will talk about the area between curves. So between curves, that means more than one, right? So that will get involved with two functions, basically. Okay, so if two areas, two curves, so it will be like this. For example, if this is for A to B, this is y is equal to f of x, right? So this is for a single function. If right now we just talk about it, can you just calculate the curve, the area between two curves? For example, if this and also like this, the second one is this one. Or g of x, sorry, g of x, right? G of x. So you can just simply, did you remember when we calculate this one, we can just follow the Riemann sum, divide it into several pieces, and try to calculate each small rectangle, and then sum them together, and then calculate its limits as the norm p is approaching 0, right? Or we can say n is approaching positive infinity. So right now we just face two curves. So the rule is still the same. We just apply that twice, right? So based on this idea, actually if you want to get the A, if you want to get A here, A will be integral from A to B. Then the upper one is f of x minus the lower one, then dx. So you can see we just apply this once, then minus g of x, because you know for each rectangle, you just divide it, the interval from A to B, several pieces, right? For each piece, we can just get the height as from here to here. If here to here, it should be f of x minus g of x, right? F of x minus g of x, and times delta x, very small x, and then sum them together, right? So you can, it's not that hard to image that. You can just image that for each sub interval. You can just calculate here to here. You can just talk about the height, and then we need to times a small portion for the interval, right? Then finally, through the integral, you just sum them together as the norm p is approaching 0. So finally, the result is just like this form, with this form. So maybe I can give you an example that with this we can have example like, please find the area of the region in the first quadrant that is bounded above by y is equal to square root of x, and below by the x-axis and the line y is equal to x plus 2. So you can see the idea is just the question just asks you to calculate some area in first quadrant. First quadrant means 第一象限, right? First quadrant. Then bounded above. So there is a bound, upper bound from y is equal to square root of y, square root of x. Then below means we have a lower bound. Lower bound means here x-axis, right? y is equal to square root of x. Then we have a lower bound is x-axis. Then we is also bounded by y is equal to y subtract 2, so that we can just also draw that it's just like this. Y is equal to x minus 2. So the question just asks you what is the areas, the size of the area, right? So if you just are given the problem just like this, just remember, just draw all curves given by the problem. So you can see we have this. Then, and also there is some important thing is you need to remember, you need to get these 3 points, because there are 3 curves, so there are also 3 intersections, right? So for this one, if you don't get this one, how can you get it? You can just simply use y is equal to square root of x, and y is equal to 0, right? So this, you can get the point is 0, 0. And of course, you also have this point. This point will be based on y is equal to 0, and also y is equal to x minus 2, right? Intersection by this line and also this line. So through this, then you can get the point should be 2, 0, right? Of course, for this point, it will based on y is equal to x square root of x, and y is equal to x minus 2. So that you can have, this part is much complicated than these 2 points, but it's still easy for you, because based on this, you can know square root of x is equal to x minus 2, so that you can have s is equal to s minus 2 squared, so that you can have s minus s squared plus 4x minus 4 is 0. So finally, you can have s minus 1 times s minus 4 is 0. So s will be 1 or 4. But 1, if 1, the point will be the fourth quadrant. So 1 will not be a legal one. So this will be a regular one, but this is okay, right? So 4 is okay. 4 is okay. 4 is okay. So if 4 is okay, finally you can get the point. Finally you can get the point is 4, 2. Right? So remember, just get these 3 points first. Coming from the intersection for these 3 curves. Then okay, we start to calculate the region. So solution 1 is our solution 1. So this solution 1 will be, let me just draw it again. My idea is here and also here, right? So my idea is I just divide it into two pieces. The first one is from 0 to 2, then 2 to 4, right? So there are 2 parts. The first part will be here. The second part will be here. So for part A, this one is A1. This is A2. So you can see the A should be based on A1 plus A2. Right? For A1, it will be integral from 0 to 2, right? For A1. But bounded by which curve? Bounded by the upper function is y is equal to square root of x, right? So it will be square root of x minus y is 0, right? So this is the power. Why this one? Because the upper curve is y is equal to square root of x, then the low curve is 0. So we just use this to subtract this so that we can get A1. For the A2 parts, it will be integrate from 2 to 4, right? And the upper function will still square root of x minus s minus 2, then dx. The second part is here is still y is equal to square root of x. But the lower part will follow y is equal to x. So finally, you have this part and this part, and then sum them together. I will not go for the detail again. So the answer will be through some calculation. Then you can get this is this one. Okay, this is solution 1. Solution 2. The curve is still with this shape, and then still here, and also here, right? And then I think you still remember the upper part is y is equal to square root of x, right? But this time, because you can see solution 1 is based on the aspect of x. However, can we just this time we can just follow the respect to y, because with respect to x, of course it will be dx. But if with respect to y, you can see we can just write one formula for this. So this time I just change my angle. Here we just follow x, but here we just follow y. So if so, y is equal to blah blah x should be changed into s is equal to y squared. And originally here is y is equal to s minus 2. We also can change it as s is equal to y plus 2. Right? From this time, we are trying to integrate this with respect to y. So you can see each slice will be like this. Instead, here is just like this, right? So this time, we will find here y is equal to y squared is the upper part. This is the lower part. So the integration is also the same one for the a should be integral from, oh no, upper part should be this one. Sorry. Upper part should be, sorry. I use my mouse. Upper part should be this one, right? You can just try to look at this curve from the angle of y. So this curve is higher than this curve. Let me just repeat again. This red curve is higher than the white curve. So the result will be the upper part will be y plus 2 minus the lower part y squared, then dy. How about the two limits? Two limits should be y from 0 to this height, right? So here we already know the point. We already know the point is 2, right? Here is 2, right? So here is 2, here is 0. So the integration will from 0 to 2. Of course, the result is still this one. And solution 3. Also this curve. Also this curve, and also this curve. This is y is equal to square root of x, and this is y is equal to x minus 2. So this time we can just think about it. We can also estimate a. A is still here, right? Could be integral from 0 to 4, right? Because 0 to 4, right? Then we can calculate the 4 part first, right? Then minus this triangle. The triangle here, this is 2. This is a right triangle. This is also 2, right? So the result is also easy. This part is easy, right? And then the result is also this one. So I just make it smaller. You can have some comparison for these 3 solutions. The first one, you just follow very traditional one with the angle of x, right? But in this case, you need to divide it into two parts. One is this part, one part. The other one is the second part, right? So divide it into A1 part to A2 part because A1 is bounded by y is equal to x, square root of x, and the lower bound is 0. But for the second part, its upper bound is still y is equal to square root of x, but its lower bound will be s minus 2, right? So it will be very intuitive way, because we always think about with respect to x. But in this case, you need to divide it into integral, so that you need to take your two integral. But if you just change your angle from x to y, the overhead is you need to convert it into, originally it will be y is equal to blah 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 s, but then we will change it into x is blah 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 y. Change the angle, right? Then the upper part will be y plus 2, means this one. This is the upper part. This is the lower part, y squared. So upper part minus lower part will be this one. But also remember, this is also very important. The two ends will be 0 to 2, 0 to 2, right? Because this we are trying to solve the same problem with respect to x, y. Okay, so then you can still get this different integral, but the final result is still the same. The last one, we are so lucky that here is just a right triangle. So why not we just can have the full form, full one, under the upper curve, y is equal to square root of x, so that we can have this, but we need to minus this right triangle. So this is a right triangle, so that you can get the result is still, okay, still blah blah blah, then you can get the result. Okay, so these three ones are acceptable, but it depends on your angle. For first one, you need to integrate the full two parts, but for the second one, you need to just face one. However, we need to change the angle from x to y, right? So there are different overhead for you. Of course, the last one is the simplest one, but sometimes we cannot always face a very ideal case like this one. Okay, so this is the section 6, and also the last part for chapter 5. Okay, and then okay, so maybe we just stop here and take a break for a while, and then come back to the classroom. Okay, chapter 6, we will talk about the application of definite integral. Actually, even we say application of definite integral, mostly in this chapter, we will just focus on the how to calculate volume. When I give you a curve, when I ask you to rotate the curve based on some axis, then can we just get the volume? Okay, so the basic idea is the volumes using cross section. So the idea is quite simple, that if there is a volume in the space, or something like that, but this is a solid. Okay, so if I want to, for example, if the start point is still x is equal to a, and the end point is x equal to b. So if I want to know the whole volume, just imagine that this is a solid in the space. So if I want to know the whole volume, if I want to know the whole volume, so what can I do? So the idea is still, can we just have a partition from x is equal to a, s0, s1, s2, blah 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 blah, here sn minus 1, sn is equal to b. So we just use this as a partition for the interval from a to b. So what is a cross section? Cross section means cross section we call it R of x with the area A of x. So cross section means, for example, if this is a cross section Rx, because you can see, if we just use the plane cut the volume, we always can get a cross section. If we call it R of x, that means you can see different x, the cutting result is different, right? So when we just cut it at some specific x, then we call it cross section Rx, and its region size is A of x. So you can see different x can have a different cross section with different area size. So the total volume will be of the case snap. Case snap means, for example, if there is a, for example, if we just focus on sk minus 1 to sk, right? Then we have two cross section. Then within this is delta sk, right? Just like Raymond sum, right? Its size almost the same as vk of A of sk times delta sk. So we can regard this snap with this cross section times delta x. Okay. So I think you just eat toast 吐司，有吃过吐司吗？对不对 ？Toast is just a cubic, but you can just imagine that if this is a toast, you can just think about each piece as the snap. So the each size will be the area of the cross section, I mean the toast, has its thickness. So if each volume is small portion, here is just like this, then as norm P is 0.0, that means we try to divide the interval into infinite number of pieces. And the V will almost the same as limit n is approaching in positive infinity, sigma k is from 1 to n, a of sk times delta sk, and the result will be integral of a to b, a of x times dx. So what is the a of x? So that means a different. Oh, let me different x. As I told you, different x. If you just use a plane to cut it, then you can have a different a of x times a small portion width. Then you can get this part. So then we just sum them together from A to B. 哦，大家想一下，这个就是当初黎曼河的时候同样的概念，它只把它延展到什么 3D 的一个 object。哦，所以你如果当初黎曼河的概念有想进去，平面上算那个面积的时候，你可以接受的话，把它想到 3D 里面的体积，其实是一样道理。假如我今天有个 volume 在这里 ，A 到 B 呢，我就切了好多点，然后每一个点用来做什么？我就是正切于它，那我就得到它的什么？在那个点上面的面积。这个面积呢，去乘以一点点的厚度，我就知道这一片贡献出来的吐司体积，对不对？就好像你们吃的吐司，有10片吐司，你总共吃了多少量的吐司？其实就是把那10片每一个体积都加进来，就是你后来吃到肚子里面的吐司的量，对不对？所以他就用这个概念。那我们再进一步来延伸，就是如果我真的要算到它惟妙惟肖的体积的话，应该怎么办？这个切割跟黎曼河当初导入的观念是一样，就是我应该把它切成什么？无穷多点，也就是每一个点啊，我都有呈现出它的切面的面积，去乘以它一点点的厚度，把它总累加起来。哦，所以最后这个公式应该会是这样子。那大家有没有发现，它会难在哪里？难在我怎么样去 model 这个切面的面积公式，对不对？这个面积公式我能够切出来，变成一个完整的公式。哦，这个事实上它是它比较难的部分。哦 ，Okay, so let me just give you the process that when you want to calculating the volume of a solid. The solid means the object, okay? The 3D object. The first thing is, please just sketch the solid and a typical cross section. So the typical cross section means A of x. So that means you need to find some way to model the cross section by A of x. So this is the most important part and also most hard should be the hardest part, the most difficult part. How can you just sketch the solid and then try to get the typical cross section first? Then the second step, is just find the formula for this A of x. Then the third step is please just find the limits of the integration. So the limit of integration means the two ends, the two bounds for the integral, right? Like from A to B. The third one is integrated A of x. So this is a typical 4 steps for that. Okay, our textbook just give you an example, and then I will draw the figure for you first. Then, okay, there is a tube. This is a can. This is a can. And its base, I mean the radius, the circle is the base, right? If we assume its radius is 3, just image that. Then I just use the plane to cut it. If I say this is x, this is y. So you can just image that. This is a plane. This is y plane. And this is a can. And with the base of a circle, this is radius is 3. Then I just use a slanted plane to cut it. So when I use the slanted, so originally we have a circle here also, right? Then we just use a slanted plane to cut it. Cut it. Cut it. Maybe not that correct. Oh, okay, correct. Okay, so that we still can have this part. Then here. Okay. The angle is 45 degrees. So you can just image that. You can just image that. This is the can, right? This is the can. Then I just try to use the slanted plane to cut it. Then after I cut it. Then there is a shape just appear like this. So it's not easy. It's not that easy to draw it. So you can see the shape just like here. There is a solid here. Can you just image it? Right now we have AR VR glasses. So in the future, you know, in the beginning when I just taught calculus, I had a dream that someday the professor teaching the calculus don't need to draw the RV shape here because it's not that easy to understand. But if you just draw where the glass is, you can just look around and understand the shape. So maybe if you are interested in that one, you can come our undergraduate student. I can buy the glasses for you, and then your responsibility is to prepare the 3D shape inside the glasses so that I can help my students, for the hackers to understand the whole solid. Of course, for me, I can set some error, right? But at least try to image it. Okay, finally, we want to calculate the solid yellow parts. Okay, no worry. I will show you the figure. Then, okay, so just image that. We need to figure out if we want to get the shape, we want to know the value of the solid. We can think about it. We need to have a cut. So if we want to get a solid, we should use a plan to cut from 0, from S is 0. Okay, let me show you. From S is equal to 0, I use a plan to cut it. Then S for somewhere, I cut it. Then finally, I cut here. S is 3. You can see different X. You can have different results. For example, if you just cut S is 0, it will become a 9. If you just cut it at S is equal to 3, it will also be a 9, but it will be a vertical line. 你可以想象吗？这块这个黄色、红色，如果用 S 等于0的时候去看它，这个黄色的截面会是什么？一条水平的线。另外一个极端是什么？在 S 等于3的时候去看得到，变成垂直线。但是 in between， 你总是可以看得出一个长方形。对你来讲，乍看之下，怎么这不会是个长方形？我会哦，你自己拿自己的杯子拿来想一想，你从这边切下去，好，想象一下啊，这个是这样对不对？你用你的截面去切它，切下去的时候，切出的这一块确实是个长方形。好 ，OK。所以这两个极端截到最极端的0的时候，它刚好是在一条水平线的长方形。最极端在 S 等于3的时候，它接出来是个垂直的线的长方形，这已经是萎缩到最后的长方形啊，那个已经都0了，那面积这体积大了，但是介于0到3之间，它总是可以切出一个长方形出来。那我们的问题是什么？我要把这个 A of X 算出来，记不记得？我说你用看着它的时候，每个地方应该会有它自己的一个 A of X。So what is the A of X? What is the A of X? Okay, so our second step is, the first step is we need to draw this one by the description. Then you should try to formulate A of X. S here is from 0 to 3. Different S can have different A of X. Okay, so if you want to calculate this A of X, okay, let me just show you that here is green, here is the white part. Then if I just cut it some X, because the degree is 45. So different X, when you just cut different X, the height will be also X. Do you agree with that? Right now, I just try to show two intersections for you. Here, if here is X, if here is X, the height will also X, because 45 degree. 45 degree. 45 degree. Then right now we have another part. This is X, this is Y. Then we have a circle. So you can just have a bird view. You just image that your eyes is here. You have top down view. Okay? Then you can see this is so if I just use my bottle to show you again. So just think about it. Think about it. This is a can, right? That image your eyes just locate here. 眼影在这里，看下来是不是一个圆 ？Right? Okay. Then again, if the cutting point is X is also here, then this is a circle, right? When you just cut it, you can see, or maybe I can use different color. Different color in orange. So this part will be 2 times square root of 9 minus s squared. Right? So that we can have, so that based on this, we can have a of x should be x times 2 times of square root of 9 minus s squared. Why is double? Because here the height will be square root of 9 minus s squared. Since it's symmetric, so we need to double. So the whole length will 2 times square root of 9 minus s squared. So this is the width. This is the width here, and this is the height here. So times length together. This is the typical area for a typical cross section. So the third part is the rectangle should runs from s is equal to 0 to s to 3 is equal to 3. Then finally, we just calculate the whole volume will be from 0 to 3. Then typical a of x will be x times 2 times square root of 9 minus s squared, then dx. The result, I also skip this part, skip the detailed calculation, then the result will be 18. So here you should try to use the substitution, right? Use the substitution for this part. Then you can just follow this form equation. This is the formula, then get the final result is 18. So here, by this example, I just want to show you that if you can get the typical A of x, then trying to integrate it from these two ends, from 0 to 3, then you can get the final result. Okay, so through this, I just decompose the rectangle into its height part and also its width part. Then you can just have a comparison. So if you want to get this view, you can just stand here. If you want to get this view, you can stand here. Let me just show you again. If you want to get this view, just stand here. Okay? If you want to get this view, just stand here. Okay? So actually about as for the calculation, it's not that hard for you because you already know the tip of substitution. But the most difficult part is how to model the typical cross-section into A of X. Okay? So this is the first one. And then I will introduce another one is solids of revolution. The first rule is the disk measure. The disk measure. So what is the solid of revolution? If the solid generated by rotating a plane region about an axis in its plane, is called a solid of revolution. 这个叫做旋转体积啊，如果你看的一些中文书的话，这个叫旋转体积。这边有很多的旋转体积、旋转表面积的问题啊，是这一章。Okay, so the idea is simple that, for example, if there is a function y is equal to square root of x, then I give you this shape, and this is the so-called plane region. Here, this is the plane region. Then about one axis, for example, if this case is, we just choose, this is the rotating axis. Then just follow this, then rotate. You can just image it, right? Just use this plane to rotate. And finally you can get solid, just like bullet. 在子弹的前身，对吧？ So that based on this idea, based on this, we just rotating, right? This is rotating. Rotating means here, just like this, right? Then you can just image that the result will be X, Y, and Z, right? And the result will be, if here is 0 and here is S is equal to 4, the result will be like this. Then from S equal to 0 to S equal to 4, then the result will be something like that. Right, after you just rotate it. And then, for example, if we just specially we focus on this part, if we focus on this part for some certain x, right? After you rotate it, you can get this shape. cross section, right? Different x can cause a different cutting results. So here it will be vanished as a point, right? But as x is increasing, you can see the cutting result becomes bigger and bigger because it's an increasing function. So the radius will become bigger and bigger. Then if you want to get the volume, you can see at each point, or we just use the height as the radius, then you can get this circle. It's a disk. So you can see this the shape is a disk. This shape is a disk. Then try to sum all these disks together. Then you can get the whole volume. So that's why we say it's a disk method. This is a disk method. So if you want to calculate the volume, the result will be integral from 0 to 4, right? 0 to 4. From 0 to 4, then pi times r square, r of x square. So you can see r means here the height as the radius, right? And you use the height r of x as the radius. And then rotate it, you can get the disk. So you will pi times r square, r of x square. So here you can just image the size, just reflect this part. Then times dx. Then you can get the total volume. Right, so it's easy. In this case, since r square, r of x should be square of x square, then dx. So it will be pi times s square over 2, then 0 to 4. Then the final result is 8 pi. So why we call it this? Of course, 1 is equal to square root of x is just an example. It's just an example. It may be different curve, but the idea is you just use this height as the radius and rotate it by x-axis, then you can get the disk. Then finally, you just sum all disks to disk, all disks together from 0 to 4, and then you can go get the whole volume. Okay, so it still follow the idea that you can see if I can get the cross section, typical cross section, I can get the typical cross section, and each disk is the typical cross section. And it is a disk, so we call it disk measure. So we can just follow this idea to get. So let's just remember that if the rotate, so right now we just rotate the shape by the x-axis. If we just rotate this curve by y-axis, will it be the same as this one? Different. Because if you just use this shape to rotate, it will be like this one. But if you use this shape rotated by y-axis, it will be like this one. So different. So please remember, what is the curve? What is the so for example, I can give you an example that also follow this one. Still this one. Y is equal to square root of x. But this time I just rotate it by x-axis. But if the rotating axis is here, then your shape will also different. So in this case, you should change y is equal to square root of x become s is equal to y squared. Okay, then each typical disk should be using r of y. That means this one as the radius. Then you can get the shape is just like this one. You will see the shape will be like this one. Different from this one, right? Different from this one. So each cross section will be here, still disk, right? So the V here will be square root of 0 to 2. If we endpoint is 2, pi r of y square. Remember, it should be dy. It should be dy. Then it will be this one. Y square dy, and the result will be, I also skip the result, the calculation about the detail of the calculation. The result will be 32 pi over 5. So you can just make a comparison for this shape and this shape. If the rotation axis is x, it will be go to this shape of the solid. But if the rotation axis is y-axis, the shape will be look like this one, right? So the final result is different. This is just like a bullet, and this is just like this shape. Okay. Okay, then I will give you an example for how to use this idea to calculate the volume of sphere. First, what is a sphere? It's a ball. It's a ball, right? So, for example, we just have a shape. We use this upper half circle, or generally it will be x squared plus y squared is a squared. So for the upper part, originally it should be the whole curve, right? But for the upper part, it will be y is equal to positive square root of a squared minus s squared, right? Then if I just, the two endpoints will be negative 2 to positive 2. Negative a to positive a. Then I just randomly pick x here. Then use the r radius. This is r of x, means different x will be causing different r of x as its radius. Then we just use this to rotate by x-axis. If our x-axis is here, then you can see the coming result will be like this one. S, Y, and Z. You can see the result will be, I need to draw the 3D object for you. So if we focus on x here, right? So finally, we can get this as is A of x. Just image that x is here. If x is here, you just use the r of x. R of x is here as a radius to rotate by x-axis. Okay, x-axis is here. Then you can get this disk, right? So A of x, this is the first part. The second part is the A of x should be pi times square root of A square minus x square squared. Right? Because we just use this high. We just use this high as its radius. And use this as its radius, we can contribute this area size. So the result will be pi times a squared minus s squared. So finally, if you want to get the v, it will be integrate negative a to positive a, all of A of x times a small portion dx. Right? So here we just get the typical cross section. We just get the area size for the typical cross section. Then the last step, we are trying to get all of this together and then get the volume. So the result will be like this one, pi a squared minus s squared dx. So that you can get pi, then a squared x minus s cubed over 3 as negative a to positive a. So finally, the result will be this one. So I believe you also memorize this formula. When I give you r, I give a as the radius for the sphere or for the ball. I believe you remember that the value will be 4 of 3 times pi times radius to power 3。这个以前应该大家有背过这个球的面积，球的体积有没有？球体积要较大，之前可能有背过，就是它是4/3的派 r 的3方。那大家知道就是说这怎么来的？当初可能只是记下来，就好像派 r 平方一样。那这个就可以从体积的观念来，这个旋转表面积，旋转体积的角度去得到哦。所以最后就是利用这样的一个想法去旋转出来哦。Okay, but do you also think about it? If I use this, but okay, just image it. Just think about if can you just also do this? This is y, and in the past we just focus on this part, right? In the previous one we just focus on this part, but can we do it as a similar way like this? And also use this rotation axis, then rotate it. So the shape is still a ball, right? The result is still a ball. Oh, sorry. Maybe I should draw it in the result still a ball. But the formula will be a little bit different. This time we will be integral the result with respect to y instead of with respect to x. Okay, but the result is still the same. The result will be still v is equal to 4/3 pi a cubed. Okay, if the radius is a, Okay, so when you go back to home, you can think about, if this time I adapt this one, can we come out the same results? Okay, so let's just see you on Wednesday.